know how to. Okay, so yes. So today, first of all, I formulate the differential game with time-varying delay. After that, we prove the sufficient condition for the existence of the open loop Nash equilibrium, and thanks to this theorem, we are able to formulate the numerical algorithm for finding the open loop Nash equilibrium in the finite steps. And we use this tool to a model of vehicle suspension, not in the advertising, but today in the vehicle suspension. So let's start with the differential game, and we analyze the game where the state is defined as a ordinary differential equation in which the difficult part is marked in the blue. I mean, this part depends on the delays, but not only on the finite a constant delay, but different in time. And also this delay depends not only on the one player, but all of the players which intend to the game. So this is our challenge for this game. And why we use this kind of equation? First of all, because in the systems there are in the literature there is proven that the time varying delays happens all the time, and usually is because of the problem with signal transmission in networks. And the second main problem with delays is because the systems have to adapt to the external conditions such as temperature, humidity, or others. And there, I also write some models with time-varying delays. It's not only the free in the literature, but it's the most recently. I mean, the time-varying delays we can apply to model of Alzheimer's disease, the model of the cardiac electrophysiology, and the model of the active vehicle suspension, which we analyze in this talk. Okay, so next, a little bit mathematics about the differential equations. So we assume that for each player, ui are Borel measurable, alpha I and beta I are Lebesgue measurable, and the state variable belongs to absolute continuous space of function. And phi and psi, this is the function which described non-linear dependence on the delay. It's Borel measurable functions, and the right-hand side of the equation is Lebesgue measurable in T. With respect to second and third variable is Lipschitz continuous, and respect with the second, third, fourth, and five is continuous. So this is the assumption which guarantee that there exists a local solution of this type of equation. Next, we defined the goal of each player, and is to maximize the following integral over all strategies ui, alpha I, and beta I. So each means that our strategy is not only u, but also delays in state and delays in the strategies. And next, we formulate a definition of the open loop Nash equilibrium the classical way. So it's means that admissible profile U bar, alpha bar, and beta bar for our game is the open loop Nash equilibrium. If for each player and for all strategies, the following equality holds. So this is standard definition. The next,
Dominika, yeah. May I ask just to be able to follow better what you are saying? So, what kind of delays here are involved? So it's not in the usual sense that you have lag.
Yes, but the lag depends on time.
So the lag depends on time, but
so it's different in times, and it's also depends on not only on the lag of one player, it's my player, but also the lag from the other players.
And this is controllable.
Yes.
Okay, so you may choose to have a longer or a smaller delay depending on the payoff that you can get.
Exactly. And on the yes, this is very important because in various systems, in many systems, this different time varying delays may causes how the behavior of the system. So that's why it's important to control this part of the system as well.
Okay, but here it's not defined as a control variable in the usual sense. You are adding something to the use that
this is the strategy the same as you.
Okay. Okay. Thank you.
Okay, so let's come back to our differential game. So because the system is not so simple as we maybe think at the beginning, so we always want to keep in mind that for each type of strategies the dynamics of the system is different. That's why we have the equation written in form, and so always we have the upper subscription W tilde I, which means it depends on the opponent's strategies. And of course, we defined the set of admissible process. So this is the set for which we have the solution of the system for. Next, we formulate verification theorem or the sufficient condition based on the dual approach. So we have some steps which we have to define. First of all, we define the dual set Pi. At the beginning, this is the set of points. After that, we fix some function yi0 belongs to the space L2. And we are looking for the dual value function vi from the Sobolev space and from the space of the continuous function on Pi, which satisfy condition 6. So how we construct this condition. So in the second line, we have the right-hand side of the differential equation. In the third line, we have the integrand. And what is the challenge in this condition? I mean, we have the supremum over u, alpha, and beta. So this is the hard part in this formulation. And next. Next, for the fix yi, also from the L2 space, we looking for the trajectory Pi depends on t, such that they are satisfied in condition 7 with the initial condition 8. And next, we try to we define the relationship between the primary game and the dual trajectories, and the relationship is described in the set 9 in the line number 9. So we are looking for point t and xi for which there are relationship between the primary trajectory and the dual trajectory. And of course, we said that trajectory Pi is dual to the xi if both are generated by the same profile of strategy. So this is also the quite important here. And now we, for given y and for given opponent strategies, we define the dual admissible set. So this is the strategies. So this is the trajectory pi for which we have equality between the primal trajectory and the dual trajectories for a given dual value function vi with the corresponding profile with the corresponding profile of strategies. And now for this, we analyze the game only in this set. So we are looking for this OpenLoop equilibrium in the set AD with these different subscriptions, and the game is defined in the 10. And for this game, we are able right now to define the sufficient conditions. So we assume that there exists a function vi which satisfies condition 6. Condition 6 means that it was the second condition with the supremum, and for some function yi0. And next we consider OpenLoop profile u bar, alpha bar, and beta bar, such that together with the corresponding trajectory xi, they belongs to our set AD, and let a dual trajectory pi with the corresponding profile of strategies satisfied equation 11 and then 11. So the equality 11. This is the quality is similar to the 6th condition, but here we instead of points we have dual trajectory pi, and we also we know that the supremum is achieved for our given profile of strategies. And of course, we have another condition. This is the 12th condition, the condition given by 12. And if those two conditions are satisfied, then we claim that the OpenLoop profile is the OpenLoop Nash Equilibrium for our game. Of course, in the set AD. So this is a little bit smaller set. Okay, so this is our sufficient condition, and based on this condition, we are able to define a numerical algorithm, and we need some definitions. So first of all, we have PIM. So this is the set. This is the subset of PI. But it consists of only the finite number of elements, and of course we have a calligraphic U IM. So this is also the set of finite element of the profile of strategies. So this is the definition of this set, and of course we define the function of best reply. We define the best reply correspondence BI in the standard way, and if we have this set and this correspondence, we are able to formulate the algorithm. So how we find the OpenLoop Nash Equilibrium for this type of game. So first of all, we choose the finite number of profiles. After that, for this, so we have a small number, so we have small set of strategies, and for this strategies, we are looking for the OpenLoop Nash Equilibrium in the small set, and using the following steps. So step 2.1, so which means that first of all, we, for each players and for each opponent's strategies and for each our strategies, we compute the value function. We compute the GI, so I mean the value of the goal function. And after, in the second step, we, for each player and for each opponent strategist, we find the best reply correspondence. And in the next step, we find the profile of strategies such that UI bar, alpha bar, and beta bar belongs to this to the best reply correspondence. So this is the classical definition of the Nash Equilibrium. And if we find it, so we are lucky. And if not, we have to find another set of another set of profiles for which we are looking for OpenLoop Nash Equilibrium. If we are in the next and in the step 3, we verify that the OpenLoop Nash Equilibrium finding for the very small set is also the Nash the OpenLoop Nash Equilibrium for the whole game. How we do it? First of all, we choose the set PIM. So this is, of course, this is the set of the finite number of parameters PI, and we choose function yi0. And for each parameter PI, we find the value function VI by solving 6. So this is the difficult part. And if we find the value functions, so based on the relationship between the primary trajectory and the dual trajectory, we are define the P. We were able to find the trajectory P over T, and P bar depends on T, and now using condition 11 and 12, if for those value function and a dual trajectory, if the condition 11 and 12 are satisfied, which means that our profile is the OpenLoop Nash Equilibrium for the whole game. If not, we have to find another set of PIM or another set of the profile. So this is our tool, and we use this tool to the vehicle suspension model. And how works this system? So first of all, we have sprung mass. So the sprung mass means that the body car. We have also the unsprung mass. So this is the tire. And the idea is that we have the spring here. It's defined by the stiffness of this spring. So this is the Ks, and we have the damping. And the idea is that the springs works that the tire with the tire is hold the road all the time if we have bumps and if we don't have the flat road. And CS and CT, I mean that this damping causes that the car is comfortable. So in this, the dynamics of the system is described by Fertin, and up to now the system there are some papers which try to control the system. So how we manage it? So we have the opposite performance. First of all, we have to have very comfortable. We want to that the car is comfortable, and on the other hand, we want to that the car is safe. But if the car is safe, so the stiffness of the spring is very high, so which means that the car is uncomfortable. So we have to find the balance between the stiffness of the spring and the damping, because we don't have any vibers of the car. And up to now, right now, in all of the non-literature, the system is controlled by only the one driver, I don't know, I'm not the expert in this vehicle, but one tool, and there is some problem. So they assume that the stiffness and the damping is constant. Our idea is that we want to go one step ahead. So what if we assume that the stiffness and the damping can change over the time? And so first of all, this is the new idea. So we want to we want to control the stiffness and the damping first of all, and we also assume that this the control works with some delay. So the delay could be because of the external conditions which car works, or because of some problems with information transmission. And so this is the main new idea. The second one, so we control the system not as an optimal control, but because we have 4 different controls, so it's natural to use not optimal control tools, but in the game theory. And that's why we have 2 players. First players, so which take the first player. The goal is the passenger safety. So how we define the safety? So which means that we minimize the suspension travel, which means we minimize the vibration of the body car and the tire. This next we minimize the tire deflection. The deflection means that the tire is hold the road all the time, so we don't have any jumps between jumps of the tire. And of course, we maximize the stiffness of the springs. We maximize the KS and KT. Why? Because they, thanks to the KS and KT, we minimize also the vibration of the car. And we have also the second player. The second player, the goal of the second player is the passengers. They focus on the passenger comfort, and of course, first of all, they minimize vibration of the body car and maximize damping. And why we need the higher damping? Because damping means that the car are very follow the road very smooth. So this is our game, and we use our tool we want to use our tool to find the Nash equilibrium for this game. And but first of all, we have to describe the system by the yes.
May I interrupt you one
yes,
more time? Sorry for that. I'm not getting the intuition why this problem is formulated as a game and not an optimal control or even a control problem.
Okay.
What makes it really necessary to have this distinction between the 2 players? Because intuitively one may think that you can put multiple objectives and try to combine them in a certain way. So can you say a few additional things regarding the necessity of using game theory here, please?
Yes, of course. So the main idea is that we have 4 controls, and they are different and they work different. They have opposite actions for the first player and for the second player. So that's why we need the game theory.
So it means here that the passenger safety and the passenger comfort are really playing a non-cooperative game.
Yes, exactly.
So it's not possible, let's say, to think about this problem as a cooperative problem, so you can solve it using some optimal control tools, saying that I would like to look for some trade-offs. I mean, I see the mathematics here, but I'm not seeing the intuition behind using a game.
Yes.
But anyway, please proceed. If you maybe you can say a few things about it later on, if you wish.
Okay, so
I think that the best will be to understand who are the passenger 1 and the passenger 2, why they are different. For me, it's only one passenger. I don't know. Perhaps you can say us which is the difference between the one passenger and the other. We can understand why.
No. So it doesn't matter. So the first player takes care about the safety of the passengers, and the second player, the goal of the second player is the comfort of the passengers.
So the passenger is not the player, in fact.
No, the passenger is not. It's not the the player are the
players,
constructor of the car.
Okay, I see. Okay, thank you.
Okay. So if we want to apply our tools, so we have to reformulate the system to the first order differential equation. So we did it. So this is the simply matrices, and with the following goal functional. So let's focus on the results right now. So first of all, we took the results, the benchmark value of the parameters, which are known in the literature. And our first question was, is it possible to analyze only the constant Ks, Kt, Cs, and Cts? I mean, but using differential games tool, is it possible to change Ks, Kt, the control, the strategies, such in this way that we get more safer and more comfortable car? So the first part of the results, we focus on the constant strategies. Further, we analyze the time varying strategies, and for those strategies, we apply different delays. One of these is 0, so without any delays, the constant delay and time varying delay. And our simulation always start with 0.0 xs 0.5 and 0.5 both are. So what does it mean? So our car starts with a very strong vibration. And the question is it possible to find better value of controls that the vibrators decline faster and without any peaks? And we, of course, analyze 3 different roads, path of the roads. I mean, we have the first one is the flat. So this is ideal world. Second is the jumps. It's like it's given by the cosinus. So it's like we have the jumps periodically. And the third road is with the one big jumps at the beginning. So this is the third types of three types of the roads. And let's talk about the results. So the first results, if we talk about the constant strategies, if we increase the value of the parameters, like from the 3 to 5%, if we talk about Ks, from 6 to 10, around the 10 Kt, and the biggest changes is for Cs. So this is the CS, this is the control of damping in the suspension system. So what we get here, we have the optimal suspension travel, and we're looking for the red line. This is the Nash Equilibrium, and we are happy when we have low numbers of peaks, and the mean value of is near the zero, and the path is also the smooth. We don't have any peaks because the peaks means that the system needs should be built with is exposed to the high forces. So the car needs to be built with the more expensive tools. So we can see that for the road number 1, so this is the flat road. So after the half of the time, the paths start to be smooth. I mean, not clearly, but I mean, it starts to be smooth. For the road with the many jumps, there is a worse situation, and we have also the smooth start to be smooth in the third case. So this now we analyze the optimal tire deflection. So this is the tire deflection. So this is the difference between the road and between the tire. And we see that after sometimes we are near the zero, so the vibration are decline, and in for all types of roads. But of course, the worst is when we consider the road with the many jumps. And if we talk about some numbers, so we see that the suspension travel decline. The best solution we find for the flat road. So it's not some unexpected results, of course, and the worst case is for the road number 2, but still we are better. We are better better than the benchmark situation. And if we talk about the tire deflection, still we have the best solution for the flat road and the worst for the second road, but still we have 10% better than the benchmark situation. If we talk about the goal functional, so we can see that we have, and we define the I1 as a total safety and I2 as a total comfort. So here we see that we are able to increase the comfort up to 10 to 15%, and not comfort, but the safety and comfort we increase up with more than 60%. So the increase is quite interesting. Next, we analyze the time varying strategies, and here are some example of the admissible strategies, because if you remember in our algorithm, first of all we have to choose a finite number of admissible strategies, and here this our example. So actually this is the this is our some example of admissible strategies for the simulation 6. Here we have, again, we compare 3 simulation. All of them is for the road 2, so the road with some peaks, and there are difference between delays. So first we have without any delays, the simulation number 5 is with constant delay, and simulation number 6 with the time varying delays. And for these admissible strategies, we get the following Nash equilibrium. This is an example for KS. Similar we have for other controls, for the strategies. And what is interesting, because they change monotonicity for the situation without any delay. We have increasing function. The Nash equilibrium is increasing in time. For the delay with constant for the simulation with constant delay, we have decreasing function. And for the last case, we have some jumps. I mean, so it's irregular case. The strategy is irregular, so we can say anything about the monotonicity. So what about the results? So the it's not so easy as for the case with the constant strategies. Still, we focus on the red line. So the red line should be near the zero without any jump. I mean yes, the idea is that without any jumps and near the zero. So here we see that without any delays. So here we have some worse part, but after some time we got the better results. And here we compare with the results, not the benchmark, but with the Nash equilibrium obtained for the constant strategies. So this is the same road, the same. So the mean value of the strategies is the same, but the difference is with the monotonicity. That's why we are able to compare the results. Okay, for this time, for the situation when we have constant delay, here we see that they are much better. And with this case where the delay is time varying, we get some results better, but at the end of this. So this is the case where the system works very very difficult situation. For the optimal tire deflection, we see that the vibration decline quite nice in all of the cases. So what about the results in the numbers? So here we see that we are able to increase the safety and the comfort in all of the cases. However, not in the same. It's not so easy. So if we focus on the suspension travel, so the best result is for the simulation without any delay. If we look at the tire deflection, the best result is for the situation with constant delay, but we have worse in the when the benchmark results for the simulation without any delays. For the time varying delays, always we have some improving, but the small one. And we also look at the peaks, because as you remember, the peaks means that the lower number of peaks, it's better. The bigger number of peaks means that there are very high forces in the system. So here we decline the number of peaks as well, maybe not in the system without delay. So we have on the same level, but with other cases we decline the peaks. What about comfort? So the comfort is we increase the comfort for the case without any delay. We we don't have much difference with the constant delay, but we have some decline in the comfort for the system with time varying delay. But at the end, if we look at the total comfort with the total safety and the total comfort, always we are able to find the better solution when with the benchmark values. And but it's not all of the situations. So we analyze other parameters and we get the similar results. So it's the result doesn't depend on the parameters. It's always we are able to get the better solution. So the conclusion is that using the game theory, we are able to find. We give the tool to construct some systems that are better in the sense that are they are more comfortable and safer. And that's all. Thank you very much for your attention.